Welcome back to TalkTensors.
It's great to be back.
As always, we're diving deep into the latest machine learning research, and this time we've got a really fascinating paper. I think you'll like this one. It's about using AI to, well, basically automate a pretty tricky part of building cars.
That's right. We're looking at how robots can be used to install wire harnesses in cars, specifically the part where they need to mate those electrical connectors. You know, those wires and plugs you see under the dash and throughout a vehicle.
Yeah, it always amazes me how many wires there are in a modern car.
Mm-hmm.
It seems like a nightmare to put them all together.
It definitely can be, and it's still a process that's largely done by hand, even with all the advances in automation we've seen in car manufacturing.
So why is that? What makes this particular task so difficult for robots?
Well, there are a few key challenges. First, the cables themselves are very flexible, which makes them hard to manipulate precisely. Second, there's a ton of variation in the types of connectors used in a car, each with their own specific shape and locking mechanism. And third, the tolerances for these connections are incredibly tight. Even a misalignment of a millimeter or two can lead to a faulty connection.
And that's a big deal in a car, where reliability is absolutely essential.
Absolutely. You don't want your electrical system failing on the highway. So the industry has been looking for ways to automate this process for a long time, but it's proven to be a really tough nut to crack.
And that's where this paper comes in. They're proposing a new approach using AI to tackle this connector mating problem.
Exactly. The core of their idea is to combine the sensing capabilities of a robot with the learning power of deep learning. Instead of just relying on vision or force feedback alone, they're integrating both, along with the robot's own sense of position, to create what they call a visuo-tactile learning system.
Visuo-tactile, that's a mouthful. So the robot is not just seeing or feeling, but doing both at the same time to figure out how to make the connection.
Precisely. And by training a deep learning model on this combined sensory data, they're able to teach the robot to understand the subtle cues that indicate a successful mating, even in the presence of real-world variations and uncertainties.
So it's like the robot is developing a kind of feel for the task, similar to how a human would learn it.
That's a great analogy. And the authors take it even further by incorporating this learned model into what's called a model-based optimizer. What that means is the robot isn't just blindly following a set of pre-programmed instructions. It can actually adapt its strategy in real time, constantly fine-tuning its movements based on the specific conditions it encounters.
So it's more of an intelligent adaptive system, rather than just a dumb robot blindly following orders.
Exactly. And the results they achieved are pretty impressive. They tested their system on a real car center console assembly task and were able to significantly improve both the speed and the reliability of the connector mating process compared to traditional methods.
That's really exciting. It sounds like they've made a real breakthrough in this area.
I think so too. This paper really highlights the potential of combining deep learning with robotics to solve complex real-world problems. It's not just about building smarter robots, it's about creating systems that can learn and adapt to the inherent messiness and variability of the real world.
All right, so we have a general idea of what this paper is about and why it's so cool. Now let's really dig into the details and try to understand the technical innovations they're proposing. Where should we start?
Well, to really appreciate the significance of this work, I think it's helpful to understand the historical context. You know, the drive to automate car assembly has been ongoing for decades. Robots are now commonplace for a lot of tasks like welding and painting, but wire harness installation has stubbornly resisted full automation.
And we talked about why that is, right? Those flexible cables, the variety of connectors, the tight tolerances, it all adds up to a really challenging task for a robot to master.
Exactly. And this paper actually does a great job of summarizing previous attempts to automate this process, highlighting the challenges and the limitations of those earlier approaches. They talk about things like vision-based systems that can be fast but struggle with changes in lighting, force feedback systems that can be robust but slow, and specialized gripper designs that try to improve alignment but might not be versatile enough for different connector types.
So they're acknowledging that they're not the first ones to try to solve this problem, but they're building upon the lessons learned from those earlier efforts.
Exactly. And they're making the case that their approach, by combining visuo-tactile learning with a model-based optimization strategy, offers a way to overcome those limitations and achieve a much higher level of performance.
Okay, so let's talk about the heart of their system, that visuo-tactile learning model. What kind of model are we talking about here, and what makes it special?
They call their model the Multimodal Trajectory Transformer, or MUTT for short. It's a type of deep learning model that's been gaining a lot of traction in robotics recently because it's really good at processing sequential data, like the movements of a robot arm.
The sequential data, meaning like a series of steps or actions over time.
Exactly. And in this case, the model is not just looking at a single snapshot of the scene, but it's taking in a stream of data from both the camera and the force sensors, as well as information about the robot's own joint positions.
So it's really getting a complete picture of the robot's interactions with the environment over time.
Right. And what makes the MUT-TT special is its ability to learn from this multimodal data. It's able to fuse the information from different sensors to create a more nuanced understanding of the task than any single sensor could provide alone.
So it's not just about seeing or feeling, but about integrating those different senses to build a more complete internal model of what's happening.
Exactly, and they trained this model on a large data set of real-world connector mating attempts, capturing all the variations and uncertainties that you would typically encounter on a factory floor.
So the robot is learning from experience, basically, figuring out what works and what doesn't through trial and error.
In a way, yes. But the key is that it's doing this learning in a very controlled and efficient way. They're not just letting the robot randomly flail around until it gets it right. They're using a sophisticated optimization algorithm to guide the learning process and ensure that the robot explores the space of possible actions in a way that maximizes both speed and reliability.
So there's still human intelligence guiding the learning process. It's not just the AI figuring everything out on its own.
Right. The humans are providing the initial program, the data set, and the optimization objectives, but the AI is doing the heavy lifting of finding the optimal strategy within those constraints.
This reminds me of something we talked about in a previous episode about the importance of human-in-the-loop learning for robotics. It's not about replacing humans entirely. It's about augmenting their abilities with the power of AI.
Absolutely. And this paper is a great example of that principle in action. Now let's talk a bit more about that optimization process. They use a technique called shadow program inversion, or SPI. Can you explain how that works?
From what I understand, it involves creating a kind of virtual model of the robot and its task, and then using that model to test out different strategies and see which one performs best.
That's a good way to put it. They call this virtual model the shadow program. It's not an exact replica of the real robot and its environment, but it captures the essential dynamics of the task in a way that's computationally tractable. They use this shadow program to optimize the parameters of the real robot's control program, things like the approach trajectory, the search pattern, and the force thresholds.
So it's like a simulation, but one that's specifically designed for optimizing the robot's behavior.
Exactly. And because the shadow program is differentiable, meaning it can be used to calculate gradients, they can apply powerful gradient-based optimization techniques to find the parameter settings that lead to the best performance.
Gradients, that's getting a bit into the weeds of calculus, but basically it allows them to find the direction of improvement in a very efficient way.
Right. And by running this optimization process offline, they can avoid having the real robot do all the trial and error in the real world, which would be much slower and potentially dangerous.
So they're using the virtual world to figure out the best strategy, and then they transfer that knowledge to the real robot.
Exactly. And they highlight a key advantage of this model-based approach. Because the optimization is happening on the program level, they can ensure that the robot's behavior remains predictable and verifiable even after it's been optimized.
So it's not like the AI is taking over complete control and doing unpredictable things. The human engineers still have oversight and can understand what the robot is doing.
Exactly. And that's really important for safety and reliability in an industrial setting. They also emphasize that their framework is designed to be integrated into existing robot programming workflows using standard industrial robot controllers. That means it's not a completely new system that companies would have to adopt from scratch. They can incorporate this AI-based optimization into their existing processes relatively easily.
That's a huge advantage in terms of practical applicability. It makes it much more likely that this technology will actually be adopted by the industry. Now, I want to talk a bit more about those experiments they did to validate their approach.
Yeah.
Can you walk us through the setup and the key findings?
Sure. They chose a really representative task for their experiments, mating 5 different types of industrial connectors commonly found in car wire harnesses into their corresponding sockets on an Audi center console. They used a standard UR5E robot arm, a type of collaborative robot that's becoming increasingly popular in manufacturing, along with a 2D camera and a pneumatic gripper. They actually designed and built a custom aluminum gripper with fingers specifically shaped to securely grasp the connector.
So they put some thought into the hardware as well, not just the software.
Definitely. They point out that having a reliable grasp on the connector is crucial for the success of the mating process. Then, for their training data, they ran the initial unoptimized robot program 4,000 times for each connector type, capturing images, force readings, and robot trajectory data throughout each attempt.
4,000 times. That's a lot of data. Why did they need so much?
They wanted to make sure they captured a wide range of real-world variations and uncertainties that could affect the mating process. To simulate those variations, they actually mounted the center console on a linear motion stage that could randomly perturb its position by a few millimeters in each direction.
Ah, so they're introducing artificial noise into this system to make the training data more realistic.
Exactly. And they also varied the robot program parameters themselves, things like the approach speed, the search pattern, and the force thresholds, to create even more variation in the data.
It sounds like they went to great lengths to make sure their training data reflected the messiness of the real world.
They definitely did, and the results show that it paid off. When they tested their trained models, they found that they could predict the outcome of a mating attempt with very high accuracy, both in terms of the robot's trajectory and the forces it would encounter. Their model was also very good at predicting whether a mating attempt would be successful or not.
So the AI had a good understanding of the task and could predict how the robot would perform. What about the actual optimization results? Did they see significant improvements?
Absolutely. Across all 5 connector types, the robot programs optimized using their SPI plus MUTT framework were significantly faster and more reliable than the original tactile-only search strategy. They saw improvements in both the cycle time, meaning the time it takes to mate the connector, and the success rate, meaning the percentage of attempts that result in a successful connection. They even conducted an ablation study to see how much data was really necessary for training, and they found that they could achieve near optimal performance with around 2,000 samples per connector, which is encouraging from a practical perspective.
It means you don't need to collect mountains of data to make this work, which could be a barrier for real-world adoption. So all in all, it seems like they've made a really compelling case for their approach.
I agree. They've shown that by combining visual-tactile learning with model-based optimization, they can achieve significant improvements in the speed and reliability of robotic connector mating, even in the face of real-world variations and uncertainties.
All right, before we wrap up, I want to spend a few minutes in our Novel Notions segment, where we like to speculate about potential future directions based on the research we discuss. What are some of the ideas that this paper sparked for you?
Well, one thing that immediately comes to mind is the challenge of dealing with deformable objects. Right now, their system focuses on mating connectors with relatively rigid bodies, but what about cases where the connector itself might bend or deform during the insertion process?
Yeah, that's a great point. Real-world wire harnesses are often quite flexible, and that could throw off the robot's calculations.
Exactly. So I think a really interesting research direction would be to extend this framework to handle those kinds of deformable objects. It would probably involve incorporating some kind of physics-based simulation into the shadow program to model how the connector might deform under different forces. So the AI would need to learn not just the geometry of the connector, but also its material properties and how it responds to pressure. That sounds like a really challenging but fascinating problem.
It definitely would be. Another potential direction, building on something we touched on earlier, is the idea of few-shot or even zero-shot learning for new connector types. Right now, they still need to collect a fair amount of data for each new connector they want to mate. But what if the robot could learn to mate a completely new connector after seeing just a few examples, or even just from its CAD model?
That would be a game changer for manufacturing, where companies are constantly introducing new products with new designs.
It definitely would. It would mean that you wouldn't need to retrain the entire system from scratch every time you had a new connector. The robot would be able to generalize its knowledge and adapt to new situations much more quickly. And there's some really exciting research happening in areas like meta-learning and sim-to-real transfer that could potentially make this possible. So the AI wouldn't just be learning to mate specific connectors, it would be learning the underlying skill of connector mating itself.
Exactly. And that's a much more powerful and versatile capability. These are just a couple of the many exciting directions that this research could lead to. I'm really curious to see what the future holds for this area of robotics.
Me too. It's clear that AI is going to play a huge role in the future of manufacturing, and this paper is a great example of the progress that's being made.
Absolutely. It highlights the potential for creating truly intelligent and adaptive robots that can handle the complexity and variability of the real world.
Well, on that note, I think it's time to wrap up this episode of Talk Tensors. Thanks so much for joining us, and a special thanks to our expert for sharing their insights on this fascinating paper.
My pleasure. It's always great to talk about cutting-edge research.
To our listeners, if you want to learn more about this work, we'll include a link to the paper in the show notes. And as always, feel free to reach out to us with any questions or comments.
We love hearing from you.
Until next time, keep exploring the world of machine learning and all its amazing possibilities.
See you then.